Hello, my name is Tyler McDaniel, and I'm going to be talking this morning about our recent study, Flexsealing BGP against route leaks, on behalf of myself, my co-authors Jared Smith and Max Schuchard, all from the University of Tennessee. So first I'm going to talk briefly about intradomain routing. There's more background in the paper if that's something you're interested in. But the internet can be viewed abstractly as a set of interconnected networks called autonomous systems, or ASs. And just as the name autonomous implies, these are networks under unique administrative control. The Border Gateway Protocol, or BGP, is the language that ASs use to communicate routes to one another. And this occurs between neighboring ASs. BGP is a path vector protocol with policies. A path vector just means that as updates move from one AS to another, they're dynamically modified. The AS path in the update is dynamically modified so that each update has a history of where it's been as it moves through the control plane. Policies just means that local network operators can apply a very flexible rule set to choose a best path to any given destination prefix. AS relationships are very important in BGP. There are two main types. Peering relationships are where neighboring ASs transit traffic between their networks without compensation for free. And then there's a customer-provider relationship where one AS pays a neighboring AS to transit its traffic to other networks. And these kinds of economic relationships give rise to something called valley-free routing. And valley-free routing simply just states that ASs will exchange routes with neighboring ASs, but that route export will be governed by economic incentive. I have a little example in this diagram. I suppose this network, called leak-dest, for reasons that will become clear later, decides to originate a route to one of its prefixes. It might do that by sending an update, a BGP update, to its provider that I'm underlining now. That provider now is incentivized to share that route with all of its connections because it learned about the route from a customer. And the more traffic it sends to that customer, that increases its own compensation. This red AS, however, if it learns about the route from its provider, it shouldn't share that route with its other peers or providers. And the reason for that is then it would be that red AS would be transiting traffic between its providers or between a peer and provider for free. And that could incur economic costs for the red AS. So this is why we call this a valley in the routing topology. And this is something we should not expect to occur. There's no technical mechanism that prevents this, but it's just AS is acting in their own interest. So I'm talking about the route leak problem, and that's what this study kind of focuses around, is mitigating route leaks. So the route leak problem is described in this RFC 7908 as a BGP update or advertisement that travels beyond its intended scope. So this is kind of a problematic definition because it gets into the intent of network operators. But it's what we have to work with. So there are 6 types, but they fall into 2 broad categories. Types 1 to 4 are valley-free routing violations, so violating that rule we saw in the last slide. And then type 5 to 6 are internal route leaks and re-origination leaks, which aren't really relevant for this study. I have actually an example leak from July of 2019, a big disruptive leak that occurred when Cloudflare sent or advertised certain prefixes to its provider, AS174, and this is a very big network in the core of the internet. That network then shared the route with another of its customers, AS33154, who's a small ISP. This network leaked a more specific of the route. It's not really important what that means, but this AS shared a route with one of its customers, AS396531. And this is when something really bad happened. AS396531 then exported that route to its other provider, Verizon. And this formed this valley in the routing topology. And more importantly, when AS701 Verizon shared this route with the rest of the control plane, a whole bunch of traffic that was destined for Cloudflare, a big content provider, was dragged over this small link in Pennsylvania. So that's bad, and it had serious impact. So this is Cloudflare's own self-reporting. I don't have absolute numbers for this, but you can see between 10:30 and about 12:30, when the leak was mitigated through out-of-band communication, Cloudflare saw a 15% reduction in inbound global traffic. For a content provider, that's bad. It's bad in pure economic terms, and it's bad reputationally as well. So these events can have serious impact on the data plane. So you might say, aren't there some mitigation systems that cover this? And there are. There's some in the table here. I'm not going to go over them because of time constraints, but there is a section in the paper that deals with this. Essentially, all the current systems either cover some specific subset of leaks, or there are deployment issues, quality incentive misalignment issues that prevent these systems from being really the final answer in preventing leaks. So in this study, we wanted to look at a relatively novel system called Peerlock from 2016. So I am aware that there are similar filtering techniques that were used before this time, but NTT documented this system in 2016, and the name is very descriptive, so I'm going to use this name at the risk of getting some emails. But Peerlock works by establishing protection rules between a pair of ASs called the protector AS and the protected AS. So the protected AS is going to actually let the protector AS know who its authorized upstreams are. And then the protector AS can install filters based on that information. So a couple things to note here. This works because ASs are sharing topological information between themselves that they wouldn't otherwise have locally. And this does not require wide cooperation between ASs to function, just between these two ASs. And so if I look at this diagram here, if I have some protected AS that shares a route with a customer, and that customer then retransmits the update to another provider, committing this value-free routing violation, the protector AS can actually filter that leak, or know that that's a leak, because the protected AS has not designated the customer as an authorized upstream. So there's another variant of Peerlock called Peerlock-lite, and again, this is something that is in the 2016 document from NTT, but probably existed before that. And this is a variant that covers only Tier 1 route leaks. Tier 1 networks are those that sit at the very top of the routing hierarchy. They have no providers. They're big global networks in general. And they have some special topological properties that we can exploit. For instance, they have no providers. So if we see a route that comes from a Tier 1 AS that then transits one of our customers before being advertised to us as a provider, we know that must be a route leak because our customer isn't providing transit for Tier 1 ASs. So this covers only a subset of potential leaks, those that transit these big networks, but it's very easy to install, and it can be helpful in preventing leaks that include Tier 1 ASs, like the one that I showed you from 2019. So our main contribution was measuring the deployment of Peerlock on the control plane, and we got interested in this because in some of our prior work, we had seen some AS path filtering that could be explained maybe by Peerlock or similar mechanisms. So the way we went about doing this was we found a target set of potential protected ASs, and then for each target we would issue control and experimental updates. The control updates were normal BGP updates in every way. The experimental updates were similar to the control, except that they're designed to trigger peer locking just for that target AS. So if someone had rules installed, some protectors had rules installed to protect the target, we should be able to detect that. And there's more details in the paper about how those are designed. Then we're going to listen for updates, for these updates, the control and experimental updates, to arrive at globally distributed collectors. And then again, because BGP is a path vector protocol, we then know when we collect the update how it's traveled through the control plane. The updates carry that history. So with that history, we can build a propagation DAG from the control update, and then compare the propagation of the experimental update with the DAG. And this will allow us to find who is filtering for the target AS. And that allows us to infer that they are peer locking or using some similar mechanism to protect the target AS. So this is just a diagram of what I just said. So we used the peering framework to issue control and experimental updates into the control plane. Those propagate somehow between AS to AS and arrive at our collectors. which are BGP stream collectors. So then we can issue an experimental update from the same points, and we can observe both people who are definitely filtering, networks who are definitely filtering. We know they received the route and they didn't propagate it, and then some also potential filtering networks who maybe they filtered it, or maybe there was networks between our advertisement points and those networks that filtered the updates. So we have both potential filters and filters that we're pretty sure about based on this technique. So to capture the uncertainty of this, we use 3 different filtering sets. We use a max filtering set that contains all ASs that were seen propagating the control update, but not the experimental update. So this would include both the potential filters and those who are almost certainly filtering. Then we have min filtering sets, which are the roots of the filtering shadows. Intuitively, there's actually a technical definition in the paper that captures this better, but essentially those ASs that we're pretty sure are filtering the update. And then we have a likely set, and this is the same as the minimum filtering set, but we're going to supplement the control DAG with inferred edges that we're pretty sure exist, but that we didn't necessarily see when we issued our control update. So our first target set were the tier 1 networks that we talked about before. These are arguably the most important networks in the routing hierarchy, and they've been implicated in some of the really bad recent leaks. So we're looking at who is protecting the tier 1 ASs with Peerlock or similar filtering techniques. So if you look at this diagram, here's some of our results from updates issued between fall of 2019 and spring of 2020. This is the ASN numbers for different tier 1 networks on X. There are 19 of them. And then on Y, we have in red how many networks that AS is protecting, and in blue, how many networks that AS is protected by out of the 19 that are in the tier 1 peering clique. So we can see there's kind of uneven but substantial deployment of Peerlock between tier 1s. I think we saw 48% of potential Peerlock rules are installed, or we saw evidence for them. So we saw some significant deployment of this within the peering clique. So a little bit more analysis on outside the peering clique. So our networks who are not tier 1s protecting tier 1 networks with Peerlock or Peerlock-lite. So what we saw here, so we split all the ASs that we saw during our experiments into their UCLA classification. So this just divides networks by the number of direct and indirect customers they have. Stubs are the smallest, and then large ISPs are the largest with 50 or more direct and indirect customers. And in blue here is the number that we saw overall during our experiments, the number we were able to observe within the window we can see of the control plane. And in red we have the number of networks that filtered at least one of our experimental updates. So you can see that we see more of the smaller networks. They're more prevalent in general, even though that they might be underrepresented within our viewing window. But we saw more and more filtering behavior for larger networks. And this is consistent with results we've had before as well. So our second target set were non-tier 1 ASs, and these are the peers of tier 1s who are not themselves tier 1s is our target set. And this allows us to look at our large ISPs being protected by this, and are we seeing penetration of these types of protection rules outside the peering clique. And so I'm not going to walk through the CDF, but essentially no, we don't see a lot of protection of these ASs. What little we do see is generally protecting networks like near tier 1 networks like Comcast. There is some protection of those types of networks, but in general we don't see a lot of Peerlock protection of ASs that are not within the peering clique, at least from our target set. We don't have a lot of time, so I'm not going to go over these experiments in detail, but we also had another set of experiments that dealt with whether or not Peerlock is effective and where additional Peerlock deployment should be placed to maximize protection, and this was done in simulation. There's more details in the paper, but we found that 90% of simulated tier 1 leaks had essentially no impact with Peerlock as it's deployed now, and uniform large ISP Peerlock-lite deployment, which is cool because there are only 308 or so large ISPs. So that's our talk. I'll take any questions.